In this tutorial, I want to introduce vector differentiation. In the first part, let me explain some basic concepts of vector-valued function. Vector-valued function v is equal to function vi multiply vector I1 plus function v2 multiply vector I2 plus until function vn multiply vector in. It can be expressed in some other ways, where the component function vi are real-valued functions of the parameter t, I are standard unit vectors. The domain of a vector-valued function is the intersection of the domain of the function vi. n equal to 2 and n equal to 3 are common forms. For n equal to 2, the vector-valued function is like this or this. Here is an example. The graph of this function is like this. We can find that it is in a two-dimension space. For n equal to 3, the vector-valued function is like this or this. The graph here is an example. The graph of this is like this. We can find it in a three-dimension space. In the second part, I will introduce vector differentiation from 5 aspects. The derivative of a vector-valued function r is defined by the limit of the differences of rt plus delta t and rt divided by delta t, where delta t approaches to 0. It's for all t that the limit exists. Let us first expand rt plus delta t and rt. Then we can commutate the term. Since the limit of the sum of two functions is equal to the sum of the limit of each function, we can get the fourth line. Moving the standard unit vector ing out of the brace doesn't influence the result. Finally, we can use the differentiation rules of real-valued functions to get the last formula. Let's explain it in the coordinate axis. The derivative of rt is a vector tangent to the curve given by the rt and pointing in the direction of increasing t values. So the general form of derivative of vector-valued function v is like this. Here is an example. If rt is equal to cosine alpha t multiplied vector I minus sine alpha t multiplied vector j. Alpha is a real number, then the derivative of it is the derivative of cosine alpha t is equal to minus alpha multiplied sine alpha t. The derivative of sine alpha t is equal to minus alpha cosine alpha t. Then the derivative of rt is minus alpha sine alpha t multiplied vector I minus alpha cosine alpha t multiplied vector j. Then I will introduce some properties of the derivative. Let r and v be differentiable vector-valued functions of t. Let u be differentiable real-valued functions of t. And let w be a scalar. The first one is the derivative of wrt is equal to w multiplied the derivative of rt. The second one is derivative of rt plus or minus vt is equal to the derivative of rt plus or minus the derivative of vt. The third one is the derivative of ut multiply rt is equal to ut multiply the derivative of rt plus ut multiply the derivative of rt. The third one is the derivative of ut multiply rt is equal to ut multiply the derivative of rt plus the derivative of ut multiply rt. The fourth one is the dot product of Vt and Rt is equal to the dot product of Vt and the derivative of Rt plus the dot product of Vt and Rt. The fourth one is the cross product of Vt and Rt is equal to the cross product of Vt and the derivative of Rt plus the cross product of the derivative of Vt and Rt. The main differences between them are we will get a number by dot product and get vector by cross product. The sixth one is x. If x equal to ut, the derivative of rut is equal to the derivative of rx and multiply the derivative of ut. Here I show how to prove the dot product rule step by step. Here I give some hints to how to prove the cross product rule. You can try to prove it by yourself. Here is an example to help you understand the properties. Then I want to introduce partial derivatives. Partial derivatives. If a vector function has several variables, we can compute the partial derivatives of the function with respect to particular independent variable. Vector functions with several variables is like this, or equivalently like this. It is the same way as we do in ordinary calculus by considering all other independent variables to be fixed parameters. Thus, the partial derivatives of the function r with respect to xi is equal to the partial derivatives of the function f1 with respect to x1 I multiply vector I plus partial derivatives of the function f2 with respect to xi multiply vector j. Here is an example. The vector-valued function is like this. The partial derivatives of the real-valued function f1 with respect to x1 is 4. The partial derivatives of real-valued function f2 with respect to x1 is 1 divided by x1. So the partial derivatives of the function r with respect to x1 is like this. The last part is some exercises. Exercise. Solution. That's the end. Thank you.